All right, let's take a look at section 3.8, which is on a topic called implicit differentiation. This is an important topic. We're going to use it the next few sections, and it's a little on the confusing side the first time you learn it. So make sure your phone is put away and you are listening carefully, taking good notes here. So I want to start off by reminding you about this notation dy dx. What does that mean? Well, you know that when you see that, it means derivative, of course. That's the derivative of a function. But more specifically, this would be the derivative of the function y. So this would be the derivative of y with respect to the variable x. And that's really important because sometimes we're going to take the derivative of the function with respect to something else. And we use this notation all the time, but don't necessarily think about it in terms of with respect to x, and that's sort of the important part in this section. Usually functions that we work with are written explicitly, and so what we mean by that is the variable y is written explicitly as a function of x. Y equals 3x squared minus 5. Y equals 2x plus cosine x. If we say f of x equals, x squared minus 7 or something like that, we use that f of x in place of the y, but either way, it's a function that's written explicitly in terms of x. But that's not always how functions are written, and not all functions are written that way at all. Some functions, or some relations, I should say, they're not even necessarily functions, may not be written this way at all. It's not possible to. And so when that's the case, these are called functions or relations that are written implicitly. For example, xy equals 1. Now sometimes we can solve for y pretty easily. Like in that first expression, I could say y equals 1 over x. In this second expression, negative 3x squared plus y equals 5, I could say y equals 3x squared plus 5. So I could rewrite those to go back to this version, but that is not always possible when it's not a function. Or not a function of x, I should say. For example, this expression, x squared plus y squared equals 9, that's a circle. There's no good way to solve for y because it's not a function. That's really what it comes down to. And every input for x will have two outputs for y. Likewise, this expression right here, this is a relation, and we can look at this in Desmos and we'll see that this is not a function. It's difficult to get y by itself here without doing a lot of crazy algebra, and even then, it's still not going to be a function. So in general, when you have y embedded in your equation like this, that means we're looking at it implicitly. And so taking the derivative of functions, and I should really be more broad here and say any equation or expressions that are written implicitly, because they're not always functions, that's called implicit differentiation. And this still tells us what the slope of the tangent line is at any given point. Take number 1 here. We have a circle, x squared plus y squared equals 1. And I still need to have the ability to find the slope of tangent lines at different locations on the graph. And so that means I still need to know how to get the derivative. So let's try this. It says differentiate this function, or this expression, I should say, with respect to x. All right, so let me come down here and write this. We've got x squared plus y squared equals 1. Anything with x is we're going to do just like we normally do. The derivative of x squared is going to be 2x plus, now the derivative of y squared, this is a little bit more involved. And what you want to think about is, let me just kind of do a little aside here. You want to think of this as sort of a chain rule. So for example, if I think of y squared as a chain rule where the inner function would be y and the outer function would be x squared, thinking of this like a chain rule, it would be evaluated as the derivative of the outer, but evaluated at the inner, so that's y, times the derivative of the inner. So here's my question to you. What is the derivative of y? Well, remember, it's with respect to x, so it's not just 1. That would be the derivative of y with respect to y. We want the derivative with respect to x. So the derivative of y with respect to x would just be dy dx, the derivative of y with respect to x. That's what we said back here, wasn't it? The derivative of y with respect to x. There it is. So the derivative of that inner function of y is just dy dx. And that's the implicit differentiation part. And then 1 over here, of course, is a constant, so the derivative is just going to be 0. Now, you always want to solve for dy dx when you do these equations, so you're going to subtract 2x here. These will involve a little bit of algebra. We've got 2y times dy dx equals negative 2x, divide by 2y. So I have, for the circle, I've got dy dx is equal to negative x over y. So the slope of the tangent line on this circle at any given point is given by this expression, negative x over y. And we could test this out at any point on the circle. Some of these points are a little bit strange number-wise, but let's just say we looked at this point. The slope of the tangent line there, you can see, should be, it's a horizontal line, so the slope should be 0, and that point would be at 0, 1. So if you put in 0 for x and 1 for y, hey, guess what? We get a slope of 0. And there it is. So you can see that. If you checked, say, over here somewhere, and by the way, I just noticed in my notes in my video, my axes are quite a bit off here. This should have a center at the origin. I think my axes must have got shifted when I cut and pasted in the document. So let's just pretend. Let's pretend that's my y-axis there. Let's just say, so let's suppose this is the point negative 1, 0. Well, the tangent line there would be vertical, so your slope would be undefined. And that fits with the equation. If you put in negative 1 over a y value of 0, you get 0 in the denominator, which gives you a slope that is undefined. And we'll practice this a little bit in class tomorrow. Let's do another example. It says, find the derivative of this expression, 2y equals x squared plus sine of y. The graph is this funny looking graph right here. So I'm going to go down the line, left to right, take the derivative. So 2y, the derivative of that will be 2 times the derivative of y, which is dy dx. So it's not just 2, you got to take the derivative of y, which is dy dx. Equals x squared, derivative would be 2x. Plus the derivative sine of y. So think of sine as your outer function, y as your inner function. Derivative of the outer evaluated at the inner times the derivative of the inner function, dy dx. And then, as I mentioned, I want you to try to solve for dy dx when you do these. So I'm going to subtract the cosine of y, dy dx to the other side. If you have multiple terms that contain the dy dx, listen to me carefully. If you have multiple terms that contain the dy dx, you want to move those to one side. So I've got 2 dy dx minus cosine of y times dy dx equals, there was a 2x on the other side. I forgot where I was at. 2x was still on the other side, so make sure you bring that down. Now, on that left side, the terms that are there both have dy dx in common. So I'm going to factor out a dy dx, and that leaves me with 2 minus the cosine of y, which equals 2x, still on the other side. And then you're going to divide both sides. So I'm going to divide both sides by 2 minus cosine y. So my derivative dy dx is equal to 2x over 2 minus the cosine of y. And that's implicit differentiation. So we'll do plenty of practices with this tomorrow in class and make sure we get the hang of it.